This video is to give you instructions on the conservation of energy with an Atwood machine activity. So I guess the first thing we should do is figure out what the heck an Atwood machine is. And an Atwood machine is actually used a lot in real life. In fact, there's one in this room at the front of the sliding whiteboards have an Atwood machine in it, which I'll show you in a minute. But the basic principle is you have two weights on a pulley, and one weight is a little bit heavier than the other weight. What this allows you to do is the goal is to be able to control something really heavy, so you put a counterweight on it, so now you don't have to work very hard to raise and lower that weight. Another classic example of where they use an Atwood machine is in an elevator. When they first made the elevators, the problem was the motor had to be so big to pull people up that the roof couldn't support it. Then somebody figured out that if you say, this is my elevator, if I put a weight hanging here, then this motor doesn't have to be that strong to pick this up because this weight is doing most of the work, or vice versa. And so that's one of the prime examples of using an Atwood machine. So let's look at what the acceleration of an Atwood machine would look like. So let's go back. We should know how to do this. Let's go back to using Newton's law. So I have two forces involved here. I have the force of gravity. If I look at the pulley, the force of gravity pulling on the left is from mass 1. The force of gravity pulling to the right is from mass 2. So I have Fg1 pulling down here and Fg2 pulling to the right. So my net force is just the difference. I subtract those. Or you could add them and put minuses in there, but it's easier just to subtract them. So the force of gravity, we all know, is mg. So I take m1g minus m2g. And this is all in your notebook. This is something you need to understand how to do this. You won't have to memorize the formula. Actually, I'm not going to give you the Atwood formula. I will expect you to be able to do 2 or 3 steps and get to whatever answer you need. But as we know, there are two ways to do net force. One is Newton's second law. The net force is always the total mass times the acceleration. So I take that, I take the total mass times the acceleration definition of the net force, and I plug it into the formula where I just took the left force minus the right force, and I get the mass, total mass times the acceleration equals my m1 minus m2g, and I solve for A. So this is a formula we're going to use in our lab today. Now you notice if m1 is close to m2, you'll see in a second when I'm done, just look at these numbers. If m1 is close to m2, that means the numerator is really small, which means your acceleration is small, which means it doesn't move very fast. Okay, it means these things. So if these things are balanced, you can control it goes up and down at a reasonable rate, as opposed to having just a pure force of gravity on one of these. We know that would be the acceleration would be 9.8. So the closer these are together, the smaller, and if you have a really large, if these are close together, and the larger they are, the slower it goes. So it's possible to have really large weights and just add a little force to the left or right, and you can pull them up and down fairly easily. And that's what we use an Atwood machine for. I said I would show you an example of an Atwood machine that's actually used in this classroom. And here it is, the sliding whiteboards. They go up and down. If you took the screws off this wooden panel, you'd see that there's a counterweight here. In fact, when they were chalkboards, there was enough friction in the pulley that you could pull it up and it would just stay there on its own. But we added the whiteboard onto the chalkboard, so now they weigh more. So now I have to prop them up with a piece of wood. I could actually, if I would increase the weight here, then I could get to where my M1 and my M2 were closer. The friction would be enough to hold it in place, and I would just have to push it up and pull it down. But this is an Atwood machine, so they get used quite a bit in real life. So with that, we've looked at an Atwood machine using Newton's second law. So that was a little bit of a review from the previous unit. So now let's look at it in terms of conservation of energy. Right now, when we let go of M1, assuming M1 is heavier, has more mass than M2, it's going to fall. So on this side of my Atwood machine, I am going to lose potential energy. M1 is going to fall this distance, and I'm going to lose that much potential energy, whatever that height is right there. On the other side, though, M2 is going to go up. So M2 is going to gain potential energy. So I'm going to lose potential energy here and gain here, but M1 is bigger than M2. So overall, the system as a whole is going to lose potential energy. So that potential energy has to go into something, and that means it will eventually go into kinetic energy. So the potential energy that I lose, so my total potential energy I get by adding the two potential energies. But now when we add the one I'm losing, when I actually punch in numbers, that's going to be a negative distance that it went, a negative h, so it will be negative. So in your lab, when you do your UG1, you're going to have a negative number there, and you're going to add it to a positive UG2. Your net result will be negative because we are losing potential energy. So as I just said, your total change in potential energy will be negative, and all that lost potential energy is going to turn into kinetic energy, which means if I just take the absolute value of my potential energy that I lost, that will tell me how much kinetic energy I gained, except in real life there's always some friction and we lose that. So in an ideal situation, I would get this out from this. And my change in kinetic energy is just equal to my kinetic energy because obviously it's not moving when we start, so my initial kinetic energy is 0. So our lab today is going to consist of measuring our change in potential energy and seeing how effective, how efficient it is at turning this lost potential energy into kinetic energy.